All right. Okay, thanks for coming, especially those of you who were at the previous talk. This is going to be about something totally different. This is actually something that I do work on as opposed to the previous thing. So I'm going to tell you about a line of work that we've been doing. Kiran is a student of mine. He's actually a local. He's a PhD student at Stanford in the MSNE department, jointly advised by my colleague Aaron Sidford and me. I'm going to tell you about this problem of profile maximum likelihood. I don't expect you to know what that means, but hopefully, the one thing I want to get across is at least what the problem is. Okay, so here's the setup. Okay, so this is a problem where you have some unknown distribution over a domain of size n. So this is a discrete problem, and the goal is to estimate some property of this distribution. For example, you might want to know what's the entropy. Think about the entropy as one particular property, but there are a bunch of other properties. And what access do you have to the distribution? So the assumption is that the access that you have is via samples. Okay, so you can draw samples from the distribution, you can look at them, and then based on that, you've got to announce some estimate of this property of interest. Okay. And I will think about symmetric properties which are invariant to the labels, permuting the labels. So, for example, if it's entropy, you don't really care about whether red has weight 0.5 and blue has weight 0.2. All that matters is something has weight 0.5, something has weight 0.2, and so on and so forth. So, there are a bunch of such properties. Entropy and its variants are one, but there's also support size and various other things which I won't actually define because they're not really important for the talk. Okay, so that's what we're interested in, but I want to tell you about the actual thing that we're going to spend most of our time on, which is this thing called profile maximum likelihood. Okay, so I'll spend a little time developing what this is, and a lot of this is the definition comes from previous work, but we need to understand what it is before we go on. Okay, so let's say we have domain of 3 elements, and let's say we get 3 IID samples. So my string of samples is A, B, A. Okay. Now, I'll say that the profile of this set of samples is just a multiset of frequencies. So in this case, I saw one element once, I saw one element twice. So my multiset has 2, 1. Okay, so the profile is 2, 1. All right? Now, if I have some underlying distribution P, for any sequence of samples, I can associate the sequence probability, which is just the probability that I get this particular sequence. So if the sequence was ABA, the probability of the sequence is just PA squared times PB. All right? Because I saw A 2 times and saw B once. All right. So far, so good. Now I'm going to define the profile probability. So the profile probability says, what's the probability that I see a sequence that has the profile, let's say in this example, 2, 1? Okay? So this is a sum over all possible sequences whose profile matches 2, 1 of the sequence probability. All right? So just to make sure that we understand this definition, in this particular case where I have a domain of 3 elements, let's try to figure out what exactly this profile probability is. So if you look at the sequences that have profile 1, 2 or 2, 1, doesn't matter. I'm not going to worry about the ordering. Well, you can have 2 A's and 1 B, 2 A's and 1 C, 2 B's and 1 A, and so on and so forth, right? So you have 6 different possibilities. And then once you fix one of these, you still have 3 different ways in which this sequence of samples could appear. If it was AAB, B could appear in the 3rd position or the 2nd position or the 1st position. You've got to sum up the probabilities of all of these sequences. So the profile probability is going to be 3 times the sum of these 6 terms. Okay? That's the profile probability. All right? So 2 things, sequence probability and profile probability. All right, so now, given any sequence, look at the profile. Now we could ask, remember, we don't know the underlying distribution, we're trying to figure out what the underlying distribution might be. So we could ask the question, what's the underlying distribution that maximizes the probability of this particular sequence of samples? Okay? That I'll call the sequence maximum likelihood. All right? It's clear? Okay. Profile maximum likelihood says, give me an underlying distribution that maximizes the probability of this particular profile. Right? So we defined previously what the profile maximum likelihood, what's the profile probability and what's the sequence probability. This says maximize over all P, this term, this expression, right? We defined the objective function in the previous slide, now we're defining the optimization problem. All right? Okay. So just to be clear, if you have a sequence ABA, profile is 2, 1, what is the sequence maximum likelihood? What's the underlying distribution that will maximize the probability of this particular sequence? Yeah, anybody? Two-thirds, one-third. The empirical distribution, right, is actually the sequence maximum likelihood distribution. It's the distribution that maximizes the probability of the sequence. Fine. What's the profile maximum likelihood? And this is not clear, right? This is somewhat unintuitive. It's really not clear. Turns out the profile maximum likelihood distribution is half-half. Okay? This is not an expected result. It's something that you really have to work out and confirm for yourself. But for now, just believe me, it's actually half-half. Okay? Let's do another example. Suppose we had a sequence whose profile was 2, 1, 1. Okay? Again, sequence maximum likelihood is the empirical distribution. It's going to be half, 1/4, 1/4. All right? What's the profile maximum likelihood? Okay? And again, this is not clear. Sit down. 1/3, 1/3. That's the obvious guess from previous one. It is uniform distribution, but it's actually uniform distribution on 5 elements. Okay? So one thing I sort of switched a little bit is that I'm not constraining the size of the domain. You don't know what the domain is. Okay? So even though I see only 3 elements, I have to allow for the fact that there might be elements in my domain that I haven't seen before, right? In fact, that's one of the big challenges in many of these estimation problems. You see a sample, you have no idea, there's probably a bunch of unseen elements. And somehow in your prediction of the property of interest, you have to account for the fact that there are probably unseen elements that you haven't seen in your sample. Okay? So the nice thing about this profile maximum likelihood is that it's in some sense predicting the existence of these unseen elements. Okay? So anyway, so I just want to give you 2 examples of.
Just comes up.
Oh, Y5?
I mean, what is 5? It's what the sum of all these plus 1 or something? I mean, what is it?
No, I mean, it just comes out from the calculation. So actually for all possible profiles all these profiles of small length, people have explicitly computed what the profile maximum likelihood is. It turns out that in some cases, this is a solution of in general, it's some solution of some algebraic equations. Okay, so you can have irrational numbers in there as well. But in general, we don't know. We don't have a good, I mean, it is the solution of some algebraic equations, but we don't have a good closed form expression for the solution, okay? Maybe just for profiles of this kind, 2 and a sequence of 1s, I could probably tell you what it is. But in general, we don't know, okay? So it's some optimization problem. It has some interesting properties. Okay, let me mention another thing. So if I fix the distribution P, and I say, what's the probability of this particular, so I fix the distribution and I fix the profile, and I ask, what's the distribution, what's the probability of this particular profile? Okay, then it turns out that the probability of this profile is actually proportional to the permanent of a certain matrix. Okay, so I said I won't use the board, but let me just use the board for this one thing. what you have to do is, you have to look at the underlying probabilities. Okay, so let's say the probabilities are P1 up to Pn, and the observed frequencies are F1 up to Fm, and then you also have to have, let's say in addition to the observed frequencies, there are a bunch of other frequencies which are all 0 that you didn't see. Let's take the full matrix where I write down n frequencies. For every element, how many times did I see it? Imagine building this matrix where the ijth entry is pi to the power of fj. Okay? Turns out that this particular objective function is closely related to, is actually proportional to the permanent of this matrix. Okay? And permanent, for those of you, I assume everyone knows, but if you don't, it's like the determinant without signs. Okay, so you sum up over all of the generalized diagonals of the entry without the sign. And again, for those who know, determinant is something that can be computed easily. Permanent is something on the other hand which is a very hard quantity to compute. Okay, so for a fixed distribution P, we actually have methods to estimate the permanent accurately. This is a celebrated algorithm of Jerome, Sinclair, and Vigoda, based on Markov chain Monte Carlo, some clever MCMC sampling. But that's not good enough for us, right? We want to find that distribution P that optimizes this quantity, and just being able to estimate the permanent very well does not actually give us a solution to our problem. Okay? And I should say one thing. We're going to be interested in approximating this profile maximum likelihood, right? That's the problem we're going to focus on. We actually don't know that it's a hard problem. In the literature, this has been cited as evidence that it might be hard, in the sense that it seems to have the properties of the permanent, and the permanent is hard. But formally, this is not really a proof that this is a hard problem. Okay, so just want to say that. Okay, so a bunch of heuristic algorithms have been proposed. I'll mention this, but there was some very nice work of Orlitsky several years ago that actually introduced this problem. So Alon and his students and collaborators came up with this notion of profile maximum likelihood, and they came up with some expectation maximization method to estimate this thing. But this is a heuristic, and we don't have any guarantees on this. More recently, there have been other works by Vandermonde who used what's called the Bethe free energy approximation of the permanent. Again, use the fact that this is really the permanent of some matrix. Let's replace the permanent by this Bethe free energy approximation and use that to define a heuristic. But again, we don't have any guarantees on this. Okay? There's another one which is a dynamic programming based thing, which is out of Stanford. A bunch of people at, very near to where I am. But again, they don't have a guarantee on this. Okay? So there are a bunch of people who have tried to approximate this, but we don't have any provable guarantees. Okay? All right. Any questions about what the problem is?
Does it signify the number of trials goes to infinity, n going to infinity? Does it become easier?
Does it become?
This is a very similar question which they have in likelihood theory, where you end up with relative entropy as a measure of the distance between, something like a distance between two probability distributions.
I see.
This looks like a finite version of that, except that you've got profiles rather than.
Yeah, it could be. I mean, what's going to happen when you have a very large number of samples is that your empirical distribution is actually going to be a very good estimate of the actual distribution. And I think that, first of all, that's going to make it unnecessary to go via this route, right? But maybe even if you're interested in this particular problem, my hunch is that it might make it easier. But I haven't really thought about this case where you have, it's possible. But I should ask you for a reference of what you're talking about later. Okay, so how is this actually, so I defined a problem in the beginning, symmetric property estimation. And then I said, let's go on a little detour. We define this kind of nice question, profile maximum likelihood. But how are the two connected? Okay, so let me tell you how they're connected. So remember, the original goal was you have this unknown distribution, you have samples, and you want to estimate some property of the distribution, okay? Now for each of these, for a variety of these properties of interest, people have figured out in excruciating detail, like in upper bounds and lower bounds on how many samples you need. Okay, so if you want interested in support, and as a result it tells you, okay, you need so many samples. If you want to get entropy, you need so many samples, and so on. And this is really nice, beautiful work. But all of these, so there are both upper bounds as well as lower bounds. So it says that you can do the estimation with so many samples, and there are distributions for which you do need so many samples. So they're sort of matching upper and lower bounds. What is epsilon? So epsilon is some measure of the accuracy with which you produce your estimate. And I'm not going to define it precisely, but let's say it's additive to within epsilon. Yeah? Okay. So for all of these properties, people have come up with very detailed methods, but one thing is that these things are all property specific. So depending on your property of interest, you have to design your custom estimator, which is tailored to that particular property. Okay. So one nice thing which motivated this profile maximum likelihood was the desire to get some kind of universal estimate. So could you somehow come up with an estimator which works for a whole bunch of properties without really worrying about the specific property of interest? Okay. So one thing is that the profile is actually a sufficient statistic for estimating symmetric properties. If you care about a symmetric property, you don't need to know the labels of the elements. All you need to know is what is the set of frequencies that you observe. Okay. So nice theorem that, again, Orlitsky and his collaborators, several years after they introduced this notion of profile maximum likelihood, they showed is that, look, for a whole bunch of properties, this is not true for all properties. There are some technical conditions that I'm going to slip under the rug. So for a whole bunch of properties of interest, if you knew what the optimum estimator was, right, there is a way of getting something which is very close to the optimum estimator by going via profile maximum likelihood. Okay, so what they said is, look, let's ignore your optimum estimator that you know about. Let's just take the number of samples that you were supposed to take. Let's compute the profile maximum likelihood distribution. Evaluate the property. If it's entropy, evaluate the entropy. If it's support, evaluate the support, whatever. Evaluate that on this profile maximum likelihood distribution and report that as your estimate. And they showed that actually this is pretty close to optimal. Okay? Roughly speaking, it requires the same number of samples as the optimum estimator. It requires maybe twice or something. The error is also very similar. Okay, so this is sort of a universal method with some caveats, which I'm not telling you about. Okay, so it doesn't work for all properties. It works for properties that satisfy some certain smoothness conditions and so on and so forth. Okay? All right. So this is great. This gives you a way to come up with kind of a universal method. One thing that's also very surprising about this result is that it turns out that you don't need to actually compute the profile maximum likelihood exactly. It suffices to even come up with the approximation of profile maximum likelihood. That's also good enough, which is really surprising, because what they're saying is, look, it turns out an exponential, like e to the n approximation is trivial. Like I think even the empirical distribution will give you a e to the n approximation. If you could get slightly better than that, e to the n to the some power, little smaller than 1. As long as you can do that, you can plug this into their theorem. Okay? Now the big problem was we didn't have any algorithm that had any sort of provable guarantee, and that's where we started looking at this question. Okay? So this is the setup. We define this nice problem, profile maximum likelihood. It seems like a cute question, sort of, one of the questions that if you're interested in discrete mathematics, might be something you might think about. But it also has this nice application that gives you this universal method for estimating symmetric properties. Okay? All right. Okay, so I won't elaborate on that comment since we're a little short on time. The main question I want to highlight is the second question here. But I'll mention two questions. So one question is, so I said, it suffices to get some kind of approximate profile maximum likelihood. And I said, even if you get some approximate profile maximum likelihood, you can get the result that Orlitsky and his collaborators proved, right? It turns out that the approximation factor does affect the end result a little bit, in the sense that when I said that, I didn't elaborate on this epsilon, which is the error parameter. Turns out that there are some conditions on epsilon. You cannot drive epsilon to be really small if you have high error, okay? And it'll be nice to get rid of this condition on epsilon. So that's one question. The other question is, well, actually, maybe the most important question is, can we actually compute this beta approximate PML distribution, right? So what do I mean by beta approximate PML distribution? There's an objective function that I define with the profile maximum likelihood problem. The optimum distribution is the one that optimizes this objective. A beta approximate PML is any distribution for whom the objective function is within a factor of beta of the optimum one. Okay? Is that clear? All right, so let me not talk about question one, I'm really going to focus on question two. Okay? All right, so the main result that we had, the first result that we had was we showed that you can get an exponential in n to the 2/3 approximation for profile maximum likelihood. And then we recently improved this to exponential in root n. So I'll spend a little time talking about this, and then I'll elaborate, say a little bit about what happens here. And I should point out the my main interest, I think, in this second result, or what I want to drive home, is not so much the fact that we improved the n to the 2/3 to root n, but there were some really fascinating connections, and the connections are the ones that I want to emphasize. Okay, so since I want to get to those connections before
But is there you think the half is optimal, or?
It's not clear. I don't really have a very strong opinion. We may have run the limit of this kind of approach, but possibly some more sophisticated approaches might work. I might speculate on that towards the end a little bit. Okay? All right. So I should say, profile maximum likelihood is one way to get universal estimators. There are other approaches, and people have pursued them. I'm not going to say much about them, but I did want to do justice to the fact that there are other approaches. It's not the only one, but I'm not going to say much about it in this talk. So again, in the interest of time, let me skip this one portion on getting rid of this condition on epsilon, and I'm going to focus most of my time on how do we get a provable algorithm for profile maximum likelihood. Okay? All right, so this is the open question. Okay, so here's how we're going to do this. Okay, so I'm going to give you a bird's eye view of our first result, which got an exponential in n to the 2/3 log n. Okay, so how does this result work? Okay, so in order to get this result, remember I said that this thing is the permanent of this particular matrix, right? Now, we're going to view this permanent in a slightly different way. Okay, so let's view the permanent in a slightly different way. Imagine that on the top, we have the frequencies. I use the f's here, but I'm going to use little n's here. Okay, so these are the frequencies with which we saw elements, and the probabilities are the pi's. So actually, pi's are unknown. We don't know them. And the nj's are things that we observed. Okay? All right, so the first thing we're going to do is we're going to do a trick that is quite natural in computer science. You do it all the time. We're going to do some discretization. So actually, the probabilities can be any values, the frequencies can be any values, but we're going to constrain them to come from some very structured sets. So we're going to use values that come from some geometrically separated. Okay, so we're going to pick values like, I don't know, half, 1/4, 1/8, so on and so forth. I'm just making this up. So we're going to choose some nice values, a small number of them, and constrain that our probability distribution only use those values. We're going to also constrain the actual frequencies that we observe. So we modified the problem a little bit in doing this, okay? But we argue that, this modification doesn't change the objective too much, right? So we changed the problem a little bit, but we didn't tweak the objective too much. Remember, we're shooting for an approximation like this. There's a lot of leeway here. So we can afford to do all these tweaks, and it doesn't really, we can get away with it, okay?
These are in a finite set.
Now p's are going to come from a finite set. Yeah. They're going to be n to the 1/3 many values, potential values for the p's, and they're going to be n to the 1/3 possible values for the n's. Okay? So we did some discretization, right? Now, what we're going to see is, what do the terms in the objective function look like? In order to get some term in the objective function, what you need to figure out is, okay, you saw so many elements, these elements appeared nj times, okay? Of all these elements that appeared nj times, which sets did they come from? Did they come from the set of elements which had this probability? Did they come from the set of elements that have this probability or this probability, and so on and so forth? So you should imagine some kind of bipartite graph connecting the probabilities to the frequencies, okay? And let's say that you had kij elements that had probability pi and appeared nj times. If I knew these kij values, if I fix these kij values, then I can write down some term that appears in my objective function, okay? And my objective function is actually going to be the sum over all such terms. Okay, so the kij values have to satisfy some kind of condition. So I know that I have so many elements that appeared nj times. This means that the sum of the kij values has to be equal to this quantity, right? Similarly, I have some condition on the bottom as well. So I'm going to sum over all feasible settings of the kij's of some function that depends on these things, right? So the next thing that we did was we said, you know what? How many possible kij values are there? Well, there are n to the 1/3 fellows on top, n to the 1/3 sets at the bottom. There are n to the 2/3 edges that go from the top to the bottom. There are exponential in n to the 2/3 possible kij values, roughly speaking. Okay? Let's replace the sum by a max. Let's approximate the sum with just the largest term. And in doing this, we lose only exponential in n to the 2/3. Because there are only exponential n to the 2/3 terms here. So we're just saying ignore all of them, just take the max.
And this is why they were n to the 1/3 terms.
That's the way that we discretized. So we discretized the top and the bottom. Sorry? Why n to the 1/3? Precisely because now that I made sure that I have n to the 1/3 elements on top and the bottom, now I know that there are only n to the 2/3 edges going across. So there are exponential in n to the 2/3 possible sets of kij values. In order to facilitate this argument, I needed to control the discretization of the top and the bottom. And there's actually two competing things. One is the discretization introduces some error. The finer the discretization, the smaller the error, okay? So at n to the 1/3, I actually balance out the error due to discretization and the error due to this. Okay, so that's what happens. Okay, so I kind of try to condense the whole thing into one pictorial slide, but this is what's going on. Now finally, we're looking at we replace the sum by the max. Now we look at this objective function. It has a whole bunch of factorial terms and so on. We replace these factorials by convex relaxations. We get a convex function. We optimize this convex function. We get a fractional solution, okay, that tells us what these kij values, that tells you what these pi's values should be, right? This is what you really care about. What is the underlying distribution? And finally, we introduce some sort of rounding algorithm that converts this into an integer solution. So these are details that we're not really going to be concerned with, but this is the overall, flow, right? We looked at our objective function. We did some grouping. We replaced the sum by the max. and we relaxed it. We got a convex problem. We solved it, and we output a distribution. And finally, this thing is an exponential in n to the 2/3 approximation. And this is what we got. Okay? So this is sort of a bird's eye view of that first result. And just to see a little bit more, the objective function that you eventually write is something of this form. It has sort of exponential in sum of xij's, log terms, and so on and so forth. So it's some complicated looking expression, but thankfully we can replace it by a convex surrogate. Okay, and we're able to control the level of approximation. Don't worry about this. We're actually not be concerned with the actual form of this expression too much. All right, so let me tell you about this new result, because that's the one that I feel could be interesting to this particular audience. And the new result is that we can actually get a little bit better, but that's not the part I want to emphasize. Okay, so let me tell you how we go about this new result. So remember, I said that the objective function for profile maximum likelihood is some permanent of some matrix. Okay, and this permanent is exactly this matrix that I defined over here. Right. So now permanent is sort of a famously hard problem to compute. To come up with an algorithm to compute the permanent is something that people have thought about for a long time. And there are some well-known approximations for the permanent. And the two approximations I'm going to talk about are the Bethe approximation, which arose in statistical physics, and the Synchron approximation, which I'll say a little bit about. Okay? All right, so let me tell you a little bit about these approximations. This is the part I'm going to focus on for the most part. There's a second part which I don't really say much about, which is once we have these approximations, we're going to again do the same steps that we had before. We're going to discretize probabilities and so on. We're going to do some sophisticated rounding. Let's not worry about all of that. Okay, so I want to focus on these connections. Okay, so what's the permanent of a matrix? Just to make sure we're on the same page. Given a matrix A, take all possible generalized diagonals and product of the entries along the generalized diagonals, sum over all these terms. Right? That's the permanent. Okay. So let me give you the form of two known approximations in the literature for the permanent. Okay. So in order to define these approximations, let's consider a doubly stochastic matrix Q. Okay. Q has the same dimensions as A, and look at the following quantity. Okay. So UAQ is sum over these terms. So you look at Q times log of AXY divided by QXY. So there's one term. There's another expression. Okay, so we're not going to be concerned with the actual expressions too much. The Bethe approximation is actually the max over all doubly stochastic matrices of exponential in this term plus this term. All right, so that's the Bethe approximation. The Bethe approximation is defined in general for more general things, but when you define it for a permanent, this is what you get.
What is doubly stochastic?
Doubly stochastic matrix is just a matrix where the rows and columns add up to 1. All entries are non-negative. Okay, so all the row sums and column sums are 1. Okay.
This is like this relative entropy. So U is like a relative, sort of like that, right? It's not quite. Yeah.
Yes, it is very much like that. That is the right sort of intuition in some sense. Okay.
Log A minus Q log. That is the
Relative entropy, yeah.
Yeah.
Good, yeah.
Okay, so this is the Bethe approximation. The Synchron approximation is a simpler to state one.
So, sorry, you said it's an approximation. So,
yeah,
so
it's not equal to the permanent, but you can actually say how close it is to permanent. I'll say that in a second. All right. Without that second corrective term, yeah. But actually, there's a very nice way to think about the Synchron approximation. This is sort of it's an objective function-based definition of Synchron, but there's a natural sort of algorithmic definition of synchron. So let's consider the following process, okay? So if you have a matrix, if you multiply an entire row by a particular factor, right? So scale a row by some factor alpha. This changes the permanent by alpha, okay? Similarly, if you scale the entire column by beta, it scales the permanent by beta. So imagine doing the following process. Let's take all the rows and scale them so that they sum up to 1. Now take all the columns and scale them so that they sum up to 1. Go back, scale the rows so they sum up to 1, go back to the columns, keep repeating this thing, all right? Now, how much does the permanent change in this process? Well, it just changes by the product of all of the multipliers that you used, right? Okay. The point is, at the end of this process, you can get arbitrarily close to a doubly stochastic matrix. So this is not straightforward, you have to prove it, but you can get, really close to a doubly stochastic matrix. So you keep doing this row scaling, column scaling, row scaling, column scaling. Finally, you get to something which is, let's say it is a doubly stochastic matrix, okay? So now the permanent of the original matrix is the product of all the multipliers times the permanent of the doubly stochastic matrix, okay? What do we know about the permanent of a doubly stochastic matrix? Well, if it's identity, the permanent is 1, okay? If it's all 1 over n, let's say, it's uniform, all the entries are uniform, then it's going to be n factorial divided by n to the n. Okay, it's like e to the minus n. Turns out that these are the extremal cases. Okay, the permanent of a doubly stochastic matrix is always between these two values. Okay, it's always at most 1 and at least e to the minus n, more or less. Okay, so this means that by this scaling procedure, we can approximate the permanent to within a factor of e to the n. Okay, and what's interesting about this, and the interest in computer science, is that this is a deterministic way to estimate the permanent, as opposed to the other approach, which gives you a 1 plus epsilon approximation. It's a randomized procedure. There's a lot of interest in trying to understand what's a good algorithm that gives a deterministic approximation to the permanent, and this synchron scaling is indeed one such method. Okay? Okay, so for our purposes, we're going to look at a slight scaling of this synchron approximation, which is just take this term and do minus n, right? Do a minus n in the exponent. Right? So all this does is that, I'll explain what this does in a second. All right, so any questions? Okay, so this is a fairly non-trivial result. Okay, this was proved by Gurwitz in 2011 by using a fairly non-trivial inequality established by Scriber in 98. And he showed that the Bethe approximation is always a lower bound on the permanent. Okay, this is not a straightforward result. I should say that now we know of a few alternate proofs of this, and some of these alternate proofs go through the theory of real stable polynomials. So there's lots of beautiful theory around this. I mean, it's sort of at the intersection of a lot of interesting lines of inquiry. Okay, and these real stable polynomials were, they've been featured in lots of breakthrough results recently. For example, the proof of the Gattison-Singer problem, came about by doing some interesting things with these real stable polynomials. So anyway, turns out that the Bethe approximation is indeed a lower bound on the permanent. Okay, and now it turns out that that scaled version of the synchron approximation, that's a lower bound on the Bethe. Okay? That's not very hard to show. It's just a straightforward consequence of the definition, but let's not do it now. So this means that the scaled synchron is also a lower bound on the permanent. All right. Now, very recently, just this year, colleague of mine, Nima Anari, and his collaborator, they showed that the Bethe approximation is at most a root 2 to the n approximation to the permanent. Okay, so remember, the Bethe is less than or equal to the permanent, and now you're saying the permanent is at most root 2 to the n times Bethe. So this says that the Bethe approximation gives you a root 2 to the n approximation of the permanent, this is actually tight. There is an example where the Bethe approximation is indeed a root 2 to the n factor away from the permanent. Okay? All right. So here's our theorem, and our theorem is the following, that if you look at the scaled synchron approximation, then this is a good approximation of the permanent. How good? The approximation factor is exponential in k log n, where k is the number of distinct columns. Okay? Now, such a result was known already if instead of exponential in k, you're willing to get exponential in n, the size of the matrix. What we showed, and this was the new result, is that we can actually improve the approximation if we know something about this matrix, if we know that this matrix has a small number of columns.
So it is 1 or something.
Yeah, if k is 1, that's great. That's fantastic. Then we get a very good, then we get a polynomial approximation. Yeah. And let me just say why we care about, why is this an interesting parameter, right? Why should you expect that the number of columns is small? So let's go back to the matrix of interest. The matrix of interest, remember, is this one, right? It's this matrix where you have probability raised to the frequency. Okay? So one straightforward observation. I have n, okay, so I have a sample of n elements. How many distinct frequencies can I have? Okay. So it's an interesting exercise, but you can show you can't have more than root n distinct frequencies. Okay. I mean, how will you have root n distinct frequencies? You'll have one element of, frequency 1, one element of frequency 2, 3, 4. You'll run out by the time you get to root n, right? Because the sum will be n. Okay. So first of all, no matter what you do, you have at most root n distinct frequencies. This means that the number of columns here, okay, distinct columns, is at most root n, right? And that's where we're going to get the exponential in root n result. Okay, and if somehow you know something more about either your distribution or of your frequencies, then you can get even better results, right? And remember that discretization trick that I told you about earlier. That actually is going to further, if needed, it can further reduce the number of distinct columns at the cost of some loss of approximation. Okay, so as a corollary, we can show that even the Bethe approximation has this exponential in number of distinct columns result. Okay, and one thing that was nice was, so we can also show these results are tight, so you can't expect to do much better than that. And I should say that the key motivation behind these results was the fact that, that objective function that I wrote down before, which I just flashed and I didn't really explain much, turns out that objective function, which we really obtained from combinatorial considerations, we said, oh, let's look at this bipartite graph, let's replace the sum by the max, let's now approximate the max, and so on and so forth. Turns out that objective function is very closely related to exactly these objective functions that you get from the scaled synchron. Okay, and this is something which was, for us, it was completely unexpected, but it was this sort of discovery of this connection which motivated these results. And as a side effect, we got these new results on the quality of the Bethe and the synchron permanence. Okay, so there are a bunch of other things that we need to do to actually drive the result, but let me not dwell on those. I think the most important things was this, to us, surprising connection between this objective function, which we got out of purely combinatorial considerations, and these other well-known approximations to the permanent, which have their origins in statistical physics. Okay, so I have a bunch of things out here which I won't elaborate on. Let me just get to the conclusion, because I think we are getting pretty close to the time. Okay, I should say the one big open problem in this work is that we apply all this machinery to get approximation for profile maximum likelihood. One embarrassing open problem is that we don't even know how to get how to show that this is actually a hard problem. So far, based on what we know, it's certainly is plausible. I think it would be surprising, but it is plausible that one could get a polynomial time algorithm for profile maximum likelihood. We haven't ruled that out yet. I think that's something that would be interesting to do. Why exponential in root n? Again, it seems to be a limitation of our technique so far. Maybe we can do better. I know that there are sort of sequences of better free energy approximations that exist in the literature, and that could be one approach, maybe, to getting better approximations. I mean, in the computer science literature, people have used sequences of convex relaxations. There are semi-definite relaxations. There are hierarchies of semi-definite relaxations, so-called Lasserre hierarchy or the sum of squares hierarchy. Entirely possible that similar such hierarchies that exist, there's something called a Kikuchi hierarchy, for example, that could be the source of some such thing, but I'm not aware of any results that have actually explored these energy approximations and know how to deal with them. So that would be very interesting. I'll leave it at that. Thank you very much for your attention.
Permanence seems to be related to the bosons, actually. If you look at particles which are sort of symmetric, their statistics is symmetric, wave function is symmetric. So, if I compute the ground state of a system of bosons, might be related to. I'm thinking about your previous lecture, fermion boson.
I see.
There are connections, of course. I mean, over the last decade, lots of connections between fermions and bosons. Free fermions and free bosons I've never seen. So, fermions are very interacting. It's most elementary, right? Maybe that works here. I don't know. But
okay.
I guess maybe one way to distill that is there a way in which you can write a permanent as a determinant, but of some other, maybe a bigger or a transformed matrix or something like that?
I know of, one result that approximates the permanent goes via determinant, and it does it in a very interesting way. What it says is, let's take your matrix of interest, let's put random plus minus signs, okay? Let's compute the determinant, and let's take the square of the determinant. It turns out the expected value of the square of the determinant is equal to the permanent, okay? And that's an interesting exercise. The variance of this is actually pretty large. So, this is a great idea, but you're going to need multiple samples to actually estimate the permanent well, okay? You need exponential in n samples because the variance is very large. But that's one explicit connection that I know between determinant and permanent. You're asking, could you somehow expand the matrix, make it larger and say it's, I don't know, yeah. I think we're going to be booted out of the room.
Yeah, we are almost done. We are essentially done. Okay, so anyway, we can chat quickly with Moses before he leaves outside. So thanks again.
All right. Thank you.